Respected session chairs and my dear delegates. I am Udaya. I am from University of Hyderabad and today I am very privileged to share with you about our exciting journey in which we are trying to develop a POC, a point of care sensor to detect food adulteration. And we have come far in our journey and I will be discussing our progress throughout this journey. Therefore, so to introduce the increasing demand, our paper for this seminar is based on the adulteration of edible oil. So the increasing demand for edible oil has led to increasing instances of adulteration in edible oil, where harmful and cheaper fatty acids are mixed with edible oils to increase the profit margin. So there is a need to have a detection method which does not need a laboratory setup, which can be easily used in a domestic environment. So therefore, for our prototype, we have taken coconut oil and the coconut oil adulteration with palmitic acid, which is the major component of palm oil, and also one of the major components in other harmful additives is taken as a adulterant. And the existing methods for detecting food adulteration, the classical methods are gas chromatography and Raman spectroscopy. However, these methods they require a laboratory environment and trained professionals to carry them out. And most importantly, they are not scalable. And therefore, for our experiment and development, we have picked electrochemical impedance spectroscopy. So electrochemical impedance spectroscopy, EIS, is a major player in study of batteries, and it is also a major player in the detection field. So in the sensor technology, our sensor technology is based on EIS. EIS is it basically studies the surface events on the electrode. So EIS, when we talk about EIS, what we have is we are applying a sinusoidal voltage to a sample. So it is similar to reading the impedance of an electrical circuit, where we apply a sinusoidal voltage to a circuit and then we read a sinusoidal current from our circuit. Therefore, the circuit will change the voltage in a certain way which is unique and which is influenced by the unique characteristics of the circuit, whether it be resistance or capacitance. And it gives, so we divide the voltage by the current and we obtain the complex impedance. It is similar to that. However, in our case, instead of electric circuit, we use our prototypical liquid. So this is the impedance of coconut oil. So this impedance spectroscopy, it's plotted, one of the ways to plot impedance spectroscopy is Nyquist plot. So in Nyquist plot, on the x-axis, we have the real component of the impedance. On y-axis, we have the complex component of the impedance. And each point of the, so impedance is similar to a semicircle. So each point on the semicircle is corresponding to a separate unique frequency. And the process flow for the detection is, we first obtain the impedance spectrum from edible oil. We use an equivalent electric circuit to fit the EIS. Then we extract the parameters of it, and then we perform regression so that we can estimate the amount of adulterant in the oil. This is the system that we have built. So in this system, we have a digital signal synthesizer which will generate any sinusoidal wave, and we have it's converted to an analog signal. Then the Z here is the test impedance. So by applying the voltage we input to our test impedance, we obtain a sinusoidal current, which we use a transimpedance amplifier to convert the current into voltage signal, and this signal is passed to filters, and then DFT is performed on the system, and by performing DFT we can obtain the frequency domain version of the current, and then we divide the frequency domain versions of the voltage and current, and thereby get the impedance. So this is how our system works. Our sensor is basically carbon based electrodes, It's a two electrode system. We have a working electrode and a reference electrode. So we have chosen a graphite based electrodes to and therefore the system is also cost effective in this area. So this is the mathematics of our system. So we have a digital signal synthesizer. So V input is given here in the first equation, and therefore the measured current is Im, which is a phase shifted, a distorted version of V input, and the transimpedance amplifier basically changes the current signal into a voltage signal, and this voltage signal is sampled, and the sampled signal is put through a DFT to convert it into an frequency domain signal. From DFT and frequency domain signal, we obtain the impedance, the real value of impedance, and imaginary value of impedance. So so now the question is, we have an impedance. So this is the impedance you can see in figure 6. So the impedance given by the blue stars is the measured impedance. So how do we make sense of this measured data? So the go-to techniques for this is by fitting it to an equivalent circuit. So we are asking, what is the equivalent circuit? What is an electric circuit that will give the same impedance as whatever is obtained from the coconut oil? So for this, we have optimized an equivalent circuit. We have searched through different many circuits, and we have ended up choosing this circuit, which you can see in figure 5. And in fitting, so these green dots, they show the fitted curve. So if we take certain values of R1, R2, Q, and omega, so this will give the same impedance that the coconut oil would give. So now that we can put the impedance into mere 5 elements, now it is easier for us to analyze the amount of adulteration or whenever this impedance circuit changes. Next thing, when we have taken coconut oil, mainly each oil, they have multiple fatty acids. So this table shows the various edible oils and various contents of the fatty acids that they have. Also, the major fatty acids we can find are oleic, stearic, myristic, and palmitic acid. Therefore, each oil has a unique composition of these fatty acids. So the technique exploits the uniqueness of these compositions. The uniqueness of these compositions affects the EIS in turn, and the difference in EIS is what is being detected. So, however, the process of fitting the measured EIS to an equivalent circuit is computationally expensive procedure. So for the development of portable systems, we had to optimize the algorithms that do the fitting process. And so we have used multiple algorithms. So each algorithm it has its own drawbacks. So coming to the main algorithm that we use when we are extracting large number of parameters is Levenberg-Marquardt algorithm. However, the Levenberg-Marquardt algorithm is very sensitive to the initial conditions, and therefore that is a significant drawback. And other algorithms like quasi-Newton algorithm, which depend on the gradient descent method, so they are computationally complex, and they have the disadvantage that they sometimes get trapped in local optimal minimas. And heuristic algorithms, although they are very good at finding the global optimas, they have a large number of tuning parameters, which makes it difficult. And tuning heuristic algorithms like genetic algorithm and other simulated annealing algorithm, so they are expensive in terms of complexity, computational complexity. And heuristic algorithms like particle swarm algorithm, they are very they are not as complex. However, they can lead to premature convergence of the solution. So therefore, what we have adapted is we have adapted a two-stage optimization method. So first, in the first stage, we perform a core search where we are using a heuristic algorithm. So we have used multiple algorithms in this table we can see. So in terms of core search, the simulated annealing algorithm and differential algorithm, we have found that this is giving a lesser, converging in less time with less function count. So function counts will look at the number of the hardware utilization, and also the function time give us the time efficiency, and the number of times that the algorithm will converge to global minima rather than converging to local minima. So we have found that in core search, first stage we do a core search, then we decide on where the global minima is for this particular set of samples. And the second stage will be a fine tuning search. In this search, we have found that the quasi-Newton algorithm and the Levenberg-Markov algorithm, they give us more efficient in terms of time and number of function counts also. So we finally ended up using the differential algorithm for a coarse search stage and Levenberg-Markov algorithm for a fine search stage. So this is the way we have used algorithms, and this is how the detection is performed. Like we have seen uh, each of the elements in the equivalent circuit, and this graph shows how each element in the equivalent circuit changes as we increase the concentration of palmitic acid in the solution. So as we start adulterating the oil more, we get so we can see that each parameter has a unique trend. So the trend is more noticeable in terms of Q1, N1, and N2. So the slope will tell us how much the adulteration has been done. So from simulation results, we have used that differential evaluation method for core search and Levenberg-Markov algorithm for fine search, and we have found out that R square of each parameter that is being given. So in our future work, so the limitation of our work is that EIS inherently it does not understand the system all by itself. So if we tell the system that the sample that we are testing is coconut oil and the adulterant that we are giving is certain thing, then the system will be able to tell how much of the adulterant is being added. However, in future work, we are trying to improve this system by combining it with other methods so that the system can do detection, standalone detection. Thank you.